4 critical points. And we'll write this down later. So later, explicitly write down. So we'll see what exactly we're heading to. So let's keep these two examples in mind. And let's redraw this picture back here again. So essentially when you're saying, when you want to calculate, let's say like df dxi, it's understood that the object on which you're defining this function and differentiating is Euclidean. In this case it was globally Euclidean. Now we know the Rn, otherwise it's locally Euclidean. So it has n local parameters which are independent. But it's not a canonical choice. You could choose another n local parameter system. So here for instance, it's a two-sphere. So although it's defined in R3, at every point you can define it by two parameters. Because it's x squared plus y squared plus z squared is 1. So for instance here, you can simply ignore the z and define it in terms of x and y. And the z is then going to be the positive square root of 1 minus x squared minus y squared. Because it's near the 1. So once you choose a set of two parameters, you can define this h entirely. So if I was trying to define the derivative of h at the north, my function is simply x y goes to z. And there is square root of 1 minus x squared minus y squared. So I know how to differentiate that with respect to x. So of course, it depends on the coordinate system. I could have chosen some other coordinate system. But the point that we'll make is we're interested in the Hessian of this object at critical point, and the linear algebraic invariance of that doesn't depend on the coordinate system. The same thing here. So you cannot literally imagine this at from R3 to R the linear map. To differentiate, it's the map itself. So that's what you expect to see. Yeah. If there are any other questions, feel free to stop and ask. So, anyway, this is like it's like a slide, like a sequence of slides. So what you do is you want to start. You have this function h. You want to start from you want to start from a very negative length and look at h inverse of minus infinity to this point. So what you want to look at is this thing. Right? So you want to look at m a. By definition, h inverse. So this is exactly the union of the level sets all the way from minus infinity to a. So in this example, this is minus 1, this is 1, right? So what should be, so if you just want to, so this is equal to 1. So what is m? This is the definition. So let's do example 1. What should be m of minus 2? This is everything which is contained in h inverse from minus infinity to minus 2, where this never hits minus 2. Right? So that should be the empty set. What about m of minus 1? This is just a single bit because the only one which gets minus 1 is the sum. That's just 1 point. 0, 0, minus 1. Well, if I choose m0, what is m0? This is everything from minus. So again, it's unfortunate. It's not this picture. Everything from minus infinity up to 0. Which is the lower hemisphere, right? So this is just this thing. So in fact, all of you know that this is basically a 2 disk. It's a closed disk. It's homomorphic to a closed disk. You can choose anything else. You could choose, let's say, m half. So what is m half? That's going to be everything all the way up to the height half. It's going to look slightly different, but not too different. It's going to look like this. So, from basic topology, you already see that these two, although they are different subsets of the sphere, they are actually homomorphic. Because they are both homomorphic to the standard 2 disk. It's like you can stretch it and map it to the unit disk, you can stretch this and map this also to the unit disk. This is also homomorphic to the 2 disk. And these are closed disks because the equator is part of this and this magnitude is part of this. Okay, so now if I go to M, let's say 2, I get the whole sphere. So I have subsumed everything and I've gone beyond that. So you can think of mostly in a very basic cartoon sense as of this board, as if saying that it's a way of using the height function which will turn out to be a Morse function, which will find what that is. It's trying to give a decomposition of the space in terms of these basic pieces and how you build one from another. So here you don't have anything. Then you get a point. Then if you go just beyond -1, you're getting things which all look like this. They look like bigger disks, but they're all disks. And then all of a sudden, when you go beyond 1, you have filled in the whole space and you have constructed the space. So if you can have some control over what happens when you go from this step to this, from this to this, these seem to be the same, and then from this to this. Then you can try to use topology to gain information, topological information from the various level sets, and what happens when you pass various critical points. So here, you see the only thing happening is when you pass this critical point, sorry, the lower one, you're all of a sudden there's nothing and then you get a disk. If you imagine not evaluating this, but actually going slightly above -1 and slightly below -1, it's like there was nothing and then you create a disk. And then all these disks are the same, but once you go beyond 1, you have created the whole. So something is happening when you pass through critical points, but when you're not passing through critical points, critical values, they all look the same, at least in this example. They all look like two-dimensional disks. Okay, so let's look at this one. So, any questions? So let's look at this one. So if we start from the bottom again, let's say we start with this empty. So this is let's say n of 1. You can choose the height and you want. Doesn't matter. So this is let's say m of -3. Right? Now once you go slightly above -2. We're getting at this. This is like n -2 plus x. Right? Just go slightly above -2. You are looking at everything which is from -infinity to -2 plus epsilon. So that's just the union of these zeros. So that's the basic. Now what happens if I go slightly above this? Because this is the next critical point and then I should be getting something which is very well known. I should be getting something like this, right? We're drawing at the same level. Right? This could be your n minus 1 because you've gone slightly above this critical. So you see here again, if I chop it up here or chop it up here, they're all of different radii, but they're all homomorphic to topological disk, which is a closed disk. Whereas if I chop it here versus here, they all look like this, except that these two might be more elongated or shorter. So this is a topological shape. Hopefully all of you recognize. This is what? Cylinder, right? Okay. Next, that's going to happen is they're going to go up here. So that's going to look like this. You've gone slightly above 1, this is what you get. So this again, well, it's not quite a cylinder. It's essentially a torus, and they have chopped off the cap. Right? This is what it is, and then once you go past this, you have built the whole thing. So if you look at n plus epsilon, this is going to be so this is kind of a sequence of things. When you have this, you have this, you have this, you have this. So what I'll indicate in this picture, and we'll again hopefully come back to this point meter is. So this is there because of a certain notion called, all of these critical points, by the way, will be attaching an integer called the index. So they are all critical points, but they are not all structured the same way. So if you are thinking of gaining some physical intuition, imagine this, that if you are looking, if you want to distinguish between these 2 points, and you are seeing this in physical experiments, how do you distinguish between these 2 points? If you're just imagining gravity, so gravity would tend to slow everything down, right? So this